Now that we have an equation for our long-run total cost function, we're going to plug in the same input prices that we had before and compare to our graphs from before. So I'm going to plug in a wage of 25 and a rent of 100 into this equation. So I've got Q over 25, and then I've got 2,500 to the 1/2. So that's 50 times Q over 25 gives me 2Q. It's not so terrible, is it? We got 2Q. That's our long run total cost function. So we can compare that to our short run total cost functions that we had before. So in the short run, when K was 1, our total cost function was Q squared over 100 plus 100. And when K was 2, our total cost function was Q squared over 200 plus 200. So how does this compare? Well, if you look here, I've put them on the graph for us, right? You'll remember this K equals 1, we started at 100 and went up. Then for K equals 2, we started at 200. We had the higher fixed cost, but then it was flatter. Well, if I plot my long run total cost function here, it's a straight line, right? 2 times Q, and it's going to go just up here tangent to my short run total cost functions. The point where they're tangent describes the lowest cost of production point if my capital is equal to 1. Of course, I could be producing other levels of output with capital equal to 1, but this is the one that would give me the most efficient production. And same here for capital equal to 2. So we want to pay attention to those tangencies, and we can find the tangencies by setting the slopes of these curves equal to each other, right? Where is this tangency happening? Because that's where we have the most efficient production in the short run. Okay, so I can find the tangency by setting the slopes equal. So the slope, the derivative of long run total cost with respect to quantity is just going to be 2, right? And then, so for K equals 1, I'm going to do this just for K equals 1. Then I take the derivative of my short run total cost with respect to quantity. That's the same as marginal cost, remember. We already did that. And that gave me Q over 50. And if I set them equal to each other, then I get that tangency occurs at a quantity of 100, which we really already knew, because that's the point where our average total cost, or short run average total cost, was minimized. And if you do that for your capital fixed at 2, you're going to get a quantity of 200 for our tangency, because again, that's the point here where your average total cost, your short run average total cost, is minimized. So like what is happening here at this tangency is that at Q equals 100, the short run production where capital is fixed at 1 is actually the optimal level of capital for that level of production. So at Q equal to 100, my K bar equals 1 is the optimal or cost minimizing level. And so anything below that level of production and I have too much capital, and anything above that level of production, I would have too little capital. So it just happens that if my capital is fixed at 1 in the short run, the cost minimizing level of production is 100. I may want to produce a quantity that's not equal to 100. And of course, that would mean that my costs in the short run would be higher than my long run costs. So the long run total cost curve shows me how total cost expands at all of the cost minimizing choices of labor and capital. But in the short run, when we might have some fixed capital, then the cost will always be higher or equal to the long run total cost, and they're equal at that point where that's actually the optimal amount of capital for that level of production. Okay, so now notice in the other graph that the long run average total cost is equal to the long run marginal cost, and that's equal to 2. And again, you see these kind of tangencies between your short run average total cost and your long run average total cost curve. So here we notice that we have this constant long run average total cost telling us that no matter how much we produce at the most efficient method of production, where we choose labor and capital to minimize our production costs, we will have an average total cost of 2. So as production increases in using this production function, there is no change in our marginal product of labor and capital, or our cost, right, per unit as we expand production. The per unit cost of production, the average total cost, remains constant as production expands. Okay. Now, that's not necessarily always the case. You may hear people refer to a situation of like an economy of scale, meaning that as we produce more, production becomes cheaper. So that would look like this graph down here, where you can see as we move out on the x-axis, as we expand production, our long run average total cost is declining. And again, if we had a fixed amount of capital in the short run, we would be along one of these short run average total cost curves here, where the tangency represents the production level that is optimal for that fixed level of capital. But these graphs, I'm really trying to show you the difference between this kind of constant long run average total cost and one that's increasing or decreasing. So when long run average total cost is decreasing, we say that we have economies of scale, or per unit cost is decreasing as production increases. And diseconomies of scale would be the opposite, where you have an increase in per unit cost of production. And of course, because it's long run, this is the cost minimizing level of labor and capital that result in this long run average total cost. But nevertheless, because of the nature of production, our per unit cost increases as production increases. All right, that's it for our cost curves videos. If you have questions, be sure to post them on the discussion board, and I will see you in class.